Hi, I'm Omkar.
I'm Aditya.
Hi, I'm Mayank.
Hi, I'm Souvik. So this is our project, which is speed prediction and object detection of a car and a video. And although we will be explaining different parts of it, we have almost equally contributed to the entire project.
This project includes two tasks. One is to predict the speed of a car from a video captured from a dashboard camera. It was a challenge released by Comma.ai, which is an autonomous car organization. Second is object detection in a video. I'll explain the first task in detail, which is to predict the speed of a car from a video. As you can see that this is a MP4 file. It's a 17 minutes video shot at 20 frames per second. Hence there are basically 20,400 frames in that video. And respectively we have 20,400 speed in train.txt file. We are using mean square error as evaluation metric. The benchmark given by comma.ai is if it is less than 10, it is good. If it is less than 5, it is better. And if it is less than 3, it is hard.
Yeah, so the initial approach used was to use the image frames converted from the video and feed them into some CNN models and train with the speed as output. However, after a few trials, it was clear that single image can't be used to predict speed, as single images have no features that can be related with the speed. For example, as you can see in this still video, we cannot predict the speed of the objects. The other way to think about the problem is that having a single image frame alone doesn't tell us much about the speed. If we think in terms of classical mechanics, you cannot estimate the position of an object based on a single frame, but to estimate the speed, you need relationship of objects in at least two frames.
While looking for a solution to the problem Aditya mentioned in the initial approach, we came across optical flow. Now, optical flow can basically be used to track the motion of an object through consecutive frames. For example, in this image, the image shows the movement of a red ball through 5 consecutive frames. And since the movement of an object would clearly be more if the speed was higher and it would be less if the speed was lower, we thought that optical flow could definitely help us in tracking the speed of an object. So for our architecture, we refer to this paper by NVIDIA published in 2016. Let's just jump into the architecture. This is the architecture. It takes as input 66 into 200 by 3, that's RGB, after which the input is normalized. Then we have 5 convolutional layers, the first 3 of which have 5 by 5 kernels and the last 2 have 3 by 3 kernels, after which we have 4 fully connected layers. As we can see, the network has about 27 million connections and 250,000 parameters. Now we have customized this a bit, which Mayank will go into in a minute. In the end, we decided to go with this architecture because it was very well appreciated in the community and because it was relatively easier to implement.
So as Omkar just explained, the input size of the NVIDIA architecture is 66 by 200, but our input image or optical flow images are around 440 by 600 in the size. We needed to reduce the size of the input data to fit to the architecture. Also, as you can see in the video, that brightness is quite low. We increased the brightness of the input images by some fractions before feeding to the CNN architecture. Then we calculated optical flow images which act as the input data for NVIDIA architecture. All the preprocessing is done using OpenCV and Python.
Implementation and training is done using PyTorch framework. As Aditya mentioned that now the input data for the CNN model is basically the optical flow image between each 2 consecutive frames, and the output data is speed itself. We have split the data into 80:20, 80 for training and 20 for validation. Here we have a data loader with batch size of 32. We tried different batch sizes, but 32 worked the best. Now this is the architecture with a couple of changes, such as we introduced a dropout to prevent overfitting. We are using p value of 0.5. We are using criteria as mean square error because this is a regression problem. Learning rate is 0.0001. We are using Adam as the optimizer. We tried different optimizers such as SGD with momentum, RMS prop, Adam, and Adam worked the best. Here we are training and calculating validation and training loss. Different hyperparameters and optimizers. The best mean square error on validation set we got is 4, which is very close to the benchmark result, which is 3 achieved by comma.ai. on the left hand side, we have the small demo where we have the actual speed versus the predicted speed. This is done on using OpenCV tool.
For our second task, we decided to do object detection in our video, and specifically to our task, the car detection in our video. Initially, we read up on literature and we saw that SSD would be a good choice for our model. And the architecture of SSD is based on the VGG16 architecture, where the fully connected layers are replaced by auxiliary convolution layers. And what we did was we used a train model in this architecture, and we used it on our video, and as you can see, it detects the cars in our video very well.